Hello, everyone, and welcome back to our PySpark series. In today's video, we're diving into the concepts of jobs, stages, and tasks in PySpark. These are the building blocks of Spark's execution model and are essential for understanding how Spark processes data in a distributed environment. By the end of this video, you'll have a clear understanding of how PySpark breaks down operations into jobs, splits them into stages, and executes them as tasks on the cluster. Let's get started. Introduction. In PySpark, jobs, stages, and tasks are the core components of Spark's execution model, forming the backbone of distributed data processing. A job represents a high level operation triggered by an action, such as collect or save a sticks file. Each job is broken down into multiple stages, which are sets of tasks that can be executed in parallel without requiring data shuffling. Finally, tasks are the smallest units of work responsible for processing individual partitions of data within each stage. Understanding how these components interact is essential for optimizing performance, managing resources, and troubleshooting issues in distributed applications. 1. PySpark job. In PySpark, a job is the highest level unit of execution triggered whenever an action such as collect, count, or show is called. It represents the entire sequence of computations that Spark needs to perform to produce the requested result. The job is initiated by the driver program, which breaks it down into smaller stages and assigns these stages as tasks to the executors. Each job may consist of one or more stages, depending on the type of transformations involved. Understanding jobs is essential for optimizing Spark applications and efficiently managing resources in distributed environments. Characteristics of a job. In PySpark, the characteristics of a job define how Spark organizes and executes a sequence of operations to fulfill an action request. Firstly, a job is initiated every time an action such as collect, count, or show is called in the application. These actions signal Spark to compute the results based on the transformations applied to the data. Each job represents the entire computation required to complete that action. Secondly, each job consists of one or more stages which are determined by the transformations used. Transformations that require shuffling of data between nodes, like group by key or reduce by key, create boundaries for separate stages. Stages represent units of parallel execution where tasks can be performed independently without requiring data to move across the cluster. Lastly, the driver program plays a critical role in managing jobs. It analyzes the operations to create a logical directed acyclic graph tag and then divides the job into stages. Each stage is further broken into tasks corresponding to partitions of the data. The driver assigns these tasks to executors, which process the data in parallel, ensuring efficient distributed execution. These characteristics highlight the structured and efficient manner in which Spark handles large-scale data processing, making it possible to optimize and scale applications seamlessly. Practical example. Example. In this example, we demonstrate how a job is triggered in PySpark when an action is executed. The process begins with initializing a Spark session using sparksession.builder.appNameJobsExample.get This step creates the entry point for Spark operations, allowing us to create data frames and interact with the Spark engine. Next, a data frame is created from a Python list containing data about individuals and their ages. The data is structured into two columns, name and age. At this stage, the data frame exists as a logical representation of the data, and no computations or data processing have occurred yet. The action df.show is then called, which triggers a job. This action requests Spark to display the contents of the data frame. In response, Spark generates a directed acyclic graph tag representing the logical operations needed to fulfill the request. The DAG is divided into stages and tasks are created for each stage corresponding to the partitions of the data. The driver sends these tasks to executors, which process the data in parallel, retrieve the results, and send them back to the driver. Finally, the driver collects the results and displays them in the console. This example illustrates how a simple action like show initiates a job in PySpark and leverages Spark's distributed computing framework to execute it efficiently. 2. PySpark stage. In PySpark, a stage is a segment of a job that groups together transformations that can be executed in parallel without requiring data movement across partitions. Stages are determined by shuffle boundaries, which occur when operations like groupie, join, or reducebacke require data to be redistributed across nodes. Within a stage, tasks operate independently on partitions of data, enabling efficient parallel processing. By breaking jobs into stages, PySpark optimizes the execution flow and ensures that data movement is minimized, improving performance in distributed environments. Characteristics of a stage. In PySpark, the characteristics of a stage define how Spark organizes and executes tasks within a job. Stages are created based on transformations and shuffle boundaries, which occur when data needs to be redistributed across nodes, such as during operations like groupie or reducebacke. These boundaries ensure that tasks within a stage can run in parallel without requiring inter-node communication, enabling efficient processing. Each stage consists of one or more tasks, where each task operates on a specific partition of the data. Tasks within the same stage execute independently and process their assigned partitions simultaneously. This structure ensures that Spark leverages the full parallelism of the cluster. When a job includes multiple shuffle operations, Spark divides it into multiple stages. Each stage handles the transformations up to the next shuffle boundary, after which the intermediate data is shuffled across nodes to prepare for the next stage. This division allows Spark to manage the complexity of data movement and ensures that distributed computations are performed efficiently. By understanding these characteristics, developers can optimize their applications and minimize performance bottlenecks caused by excessive shuffling. Practical example. This example demonstrates how PySpark divides a job into multiple stages based on the sequence of transformations and the presence of shuffle operations. The process begins with the initialization of a Spark session. The entry point for Spark applications using Spark session.build.appname stage is example.get or create. A sample dataset containing employee details, including their names, departments, and ages, is then loaded into a data frame. The execution pipeline involves the following steps. Group by department, the transformation df.groupbydepartment.count counts the data by the department column and counts the number of employees in each department. This operation involves a shuffle where data is redistributed across nodes to group records with the same department. Since shuffling requires inter-node communication, this step creates a new stage. Filter departments, the next transformation df underscore group dot filter df underscore group count 1 filters the group data frame to retain only departments with more than one employee. This transformation does not involve shuffling but is executed in a separate stage because it operates on the output of the previous shuffle operation. Finally, the show action triggers the execution of the pipeline. Spark generates a job for this action and divides it into two stages. The first stage handles the grouping and shuffling of data, while the second stage processes the filtered results. Tasks within each stage operate in parallel on partitions, ensuring efficient distributed computation. The results are then collected by the driver and displayed in the console. This example highlights how PySpark organizes a job into stages to manage complex transformations and optimize distributed data processing. 3. PySpark task. In PySpark, a task is the smallest unit of work within a stage. Each task is responsible for processing a single partition of data and is executed by an executor on a worker node. A stage consists of multiple tasks where each task operates independently on its assigned partition, allowing for parallel execution. Tasks perform the transformations and actions defined in the stage, ensuring that computations are distributed efficiently across the cluster. By breaking a stage into tasks, PySpark maximizes resource utilization and achieves high performance in distributed data processing. Characteristics of a task. In PySpark, the characteristics of a task define how work is distributed and executed within a stage. Each task is executed by an executor on a worker node where it processes a single partition of data. This distributed approach allows tasks to operate independently and in parallel, making the execution highly efficient. Tasks are designed to apply the same transformations to their respective partitions of data. For example, if a stage involves filtering rows or mapping values, each task performs these operations on its assigned partition. This uniformity ensures that the computations remain consistent across all partitions, contributing to predictable and reliable results. Task execution is parallelized across the cluster, meaning multiple tasks can run simultaneously on different worker nodes. This parallelism leverages the cluster's computational resources, significantly improving performance and reducing the time required to process large data sets. By breaking down stages into tasks, PySpark enables scalable and efficient distributed data processing. Practical example. This example demonstrates how PySpark divides the workload into tasks and executes them across a cluster. The process begins by initializing a Spark session using sparksession.builder.appname tasks.example.getRate. A sample dataset containing employee information is then loaded as an RDD with 4 partitions, ensuring that the data is divided into chunks for distributed processing. The RDD is converted into a data frame with columns name, department, and age for structured data operations. The number of partitions in the data frame is verified using df.rdd.getNumPartitions, which confirms that there are 4 partitions matching the RDD configuration. This partitioning ensures that tasks will be distributed across the cluster with one task assigned to each partition. The execution pipeline begins with the transformation where a new column age underscore plus underscore 1 is created by adding 1 to the age column using df.withColumn. This transformation does not involve shuffling, so it can be executed independently by tasks on their respective partitions without data movement. Next, a groupy operation is applied to group data by the department column and calculate the average value of age underscore plus underscore 1. This operation requires shuffling as data must be redistributed across partitions to group records belonging to the same department. To optimize this shuffle process, the number of shuffle partitions is set to 4 using spark.conf.set spark.sql.shuffle.partitions4. Finally, the action df underscore group dot show triggers the execution of the transformations. Spark creates tasks for each stage of the pipeline and assigns them to executors. In the first stage, tasks process the partitions independently to compute the age underscore plus underscore 1 column. In the second stage, tasks handle the shuffle and aggregation, ensuring that group data is processed accurately. The results are displayed in the console, showing the average age underscore plus underscore 1 for each department. This example highlights how PySpark divides transformations into tasks, executes them in parallel, and efficiently handles operations requiring shuffling across partitions. Summary, job, stage, and task. In PySpark, the execution model is built around three core components: jobs, stages, and tasks, each playing a unique role in distributed data processing. Job. A job represents the complete computation required to fulfill an action. Actions such as collect, show, or count trigger a job, which encompasses all the transformations and operations necessary to produce the requested result. For example, calling df.show triggers a job that Spark executes by analyzing the transformations applied to the data frame, dividing the work into stages and tasks, and processing the data across the cluster. Stage. A stage is a subset of a job and consists of a sequence of transformations that can be executed without requiring data shuffling. Stages are created based on shuffled boundaries in the directed acyclic graph tag of operations. For instance, a transformation like group B introduces a shuffle operation to group similar keys together, which creates a new stage. Each stage can include multiple tasks that process partitions independently, ensuring parallelism within the stage. Task. A task is the smallest unit of execution in Spark and operates on a single data partition. Tasks are created for each partition in a stage and are assigned to executors for execution. For example, during a group B operation, tasks in the first stage process partitions locally, while tasks in the subsequent stage handle the shuffled data to compute grouped results. Each task applies the transformations defined in its stage to the data partition it processes, ensuring efficient distributed computation. Together, jobs, stages, and tasks form the backbone of PySpark's distributed computing framework, enabling it to process large datasets efficiently by breaking down computations into smaller manageable units. Uh, Example of job, stage, and task flow. This example demonstrates how PySpark organizes a computation into jobs, stages, and tasks to process data in a distributed environment. The process begins with the initialization of a Spark session, which serves as the entry point for executing PySpark applications. A sample dataset of employee details, including their name, department, age, and salary, is loaded into a data frame for further processing. To ensure distributed processing, the data is repartitioned into four partitions using the repartition 4 method. This step divides the data into manageable chunks, where each partition can be processed independently by tasks. The number of partitions before and after repartitioning is printed to confirm the setup. The first transformation df.filter call age greater than 30 filters employees older than 30. This transformation does not require shuffling and can be executed within a single stage. The second transformation, df underscore with underscore bonus dot with column adjusted underscore salary, call salary plus 500, adds a new column adjusted underscore salary by increasing each employee's salary by 500. This operation also operates on partitions without requiring data movement. The third transformation, Ruby department.av adjusted underscore salary, groups the filter data by department and calculates the average adjusted salary. This transformation involves a shuffle as data must be redistributed across partitions to group employees by department. The shuffle creates a new stage in the job. Finally, an action is triggered with df underscore group.show, which displays the group results in the console. Spark analyzes the transformations, generates a directed acyclic graph tag, and divides the computation into stages and tasks. Another action, df underscore group dot count, triggers a separate job to count the number of rows in the group data frame, demonstrating how multiple actions can generate independent jobs within a PySpark application. This example highlights PySpark's execution model, where transformations define the logical plan and actions trigger physical execution. The division into jobs, stages, and tasks ensures efficient distributed processing while leveraging the cluster's computational resources. And that's it for today's video on jobs, stages, and tasks in PySpark. We hope this breakdown gave you a better understanding of Spark's execution flow and how it efficiently processes large datasets. If you found this video helpful, don't forget to hit the like button, subscribe to our channel for more PySpark content, and turn on the notification bell to stay updated. Thanks for watching, and we'll see you in the next video.